Word embedding has been one of the buzzwords in NLP for the last 5-10 years. If you've been working on NLP or simply heard about NLP, it is very likely that you've run into word embeddings more than once. So in this tutorial, we are going to shed light in some of the most important aspects in word embeddings. What are word embeddings? Why are they so popular? Or what are the most commonly used methods in the last 5-10 years? These are some of the questions that we are going to try to answer in this short overview. This is the outline of the presentation. We will start with the most traditional word vector representation, the so-called count-based models, and then move towards the most trendy branch, that is the predictive models, which is actually also the branch that has brought the name word embeddings itself. Then we will move towards different aspects of word embeddings that are often considered and are also useful in many applications. First is a character-based embeddings, or how actually character play a crucial role in the representation of words in many cases. Knowledge-enhanced word embeddings, or how to use knowledge sources or lexical sources to improve the quality of word embeddings. And finally, cross-lingual or multilingual word embeddings. Because not everything in NLP is in a single language, or English for that matter, but there are many languages and many applications that are actually multilingual in nature. And this is where cross-lingual embeddings come into play. And finally, as I was mentioned at the beginning of the video, I'm going to explain also what are the main use cases of word embeddings and why actually they are useful. And briefly also discuss some of the main ways to evaluate them. So what are word embeddings? I think we can explain this better with a picture. Word embeddings represent words in a vector space, where actually each point in the vector space is a word. And then they satisfy different properties, but being the most important of them is like similar words, they occur close in the vector space. So for example, here we have like a small vector space when we have different animals. And what we would expect with a word embedding space is like, for example, the big cats like cheetah, jaguar, tiger, panther, leopard. They will be close in the vector space. So this looks quite nice, but then how actually are we going to learn these word embeddings? So this is the main procedure, but there are of course also others. First, we gather a very large corpus that can be a general domain corpus, that has been one of the most successful approaches, or it can be maybe just a corpus of a given domain, for example, the one of animals, as I showed before. Then what we're going to do is each word is going to occur in different contexts. Like here we have the example of London, and doing some mathematical operations, where you're going to end up is having London with a vector that is basically a set of numbers. So what kind of properties you are going to learn from the corpus? So strangely enough, the main ideas from word embeddings, date back from the 50s or even earlier, no? Where they say actually the words occurring in similar contexts tend to have similar meanings. So with this hypothesis is how actually even the modern word embedding approaches behave, and they try to fill this property by different means. But basically this is the main property, or one that is the most important in most common approaches. Let's start with the most traditional model, that is count-based models. How they work? So this was briefly discussed in the introduction, no? And basically one of the most common ways to represent a document or some kind of text is the term document matrix, where you have like rows, like it's an example, they are going to be terms or words like dog, internet, cartoon, cartoonist. And in the columns, what we are going to have is different documents. So the documents talking about different things. And here the counts, basically they represent simply the number of times that a word occurs in a certain document. So for example, dog occurs 3 times in the first document and 10 times in the second document, and doesn't occur in all the other documents. As usual, these are raw frequency, but you can also use some weighting schemes such as DF-IDF or lexical specificity. and this also will work. But the general idea is as simple as that, and just counting the frequency of words in a document. And basically, finally, so what is going to be the word vector? The word vector is simply defined as the vector of counts over the documents. So here the rows here in this image. What is another way to get it? Because sometimes it's not so easy to partition a whole corpus in documents. So the documents are going to be of different sizes, or not always we want to have what we call documents. So one simple idea is simply like a concordancer. You extract all the sentences where doc occurs and see what is the context of doc, no? And basically you are going to see that doc is going to occur often with words like pet, animal, cat, and maybe something that is unrelated is not going to occur that much, no? Like a cartoonist in the other example that we had before. So we will end up with a co-occurrence-based vector as follows. Here doc will be simply the vector where each position in the vector represents another term, or another word in this case. So for example, doc is going to have 10 in the place of animal, 25 in pet, because they occur quite often, but then for other words, it's going to be, this number is going to be lower. And for many of them, this number is going to be actually 0. So one of the properties of this vector is sometimes they are also quite sparse. But they are also quite high dimensional, no? That is one of the main problems of these models. So here, even if it's high dimensional, you can just actually represent it in a vector space, and you will have something like in the image where dog is going to be expected to be similar to other mammals, or to like cat, for example, or even the word mammal, but it's going to be far from things like cartoonist. And how can we solve this problem of the high dimensionality? So this is not a huge problem. There are many techniques, mathematical techniques, to try to reduce the number of dimensions. So what are the ways that we can reduce? Here there is one example. I'm not going to get into details, like Raman indexing, non-negative matrix factorization, singular value decomposition, latent Dirichlet allocation, or neural networks, what we call the so-called predictive models. And basically this is what I'm going to now focus on. But if you are interested in the other methods, so you can have them there and investigate on your own. So what are the predictive models, and why they are different than the count-based models? As I mentioned, the predictive models are not very different in nature than the count-based models, and in fact there has been some research showing that they share more properties than they differ. But this is one example, the word2vec of Nikolov et al. In 2013, that revolutionized actually the field of NLP, and it's been very popular. So how it works? So in that work, they proposed two different models, SIBO and SkipRAM. In the case of SIBO, the idea is very simple. So you have an input sentence, where you have here represented by W, and you have an output word that is actually the word in the middle. Like in our example, for example, could be dog. So simply what we are going to do is take into account the context. So the words that occur with dog in the sentence, we have to predict the word dog. So in this case, this word here, the output. And by learning this millions of times in the whole corpus, you are going to get something that actually resembles what we saw with the count-based models, where similar words are going to be close in the vector space. And this can be learned with different architectures, like the word2vec. One of the positive things is that it was a very shallow architecture, so it was also very efficient to run, and anybody could run that even in your own laptop, with a very large corpus. And then SkipRAM is a very similar idea, and it's been actually a bit more successful, where it can seem a bit more counterintuitive. So here we have the word in the middle, that in our running example is going to be dog, and what we're going to predict is the word in the context of dog. So instead of trying to predict word, we're going to predict the context. And this has been also shown to learn very, very interesting word representations. And one of the things that was very popular with this model is like word analogies, that surprisingly, because this was not learned throughout the process, you get some kind of regularities in the vector space. Like for example, like country of relations, you are going to find out like China, Beijing, Russia, Moscow, Japan, Tokyo. They are going to have like a similar they are going to represent like more or less the same the same shape, no? So for example, you are going to have parallel lines like Johnny in China with Beijing or Russia with Moscow. Of course, this is not as simple as it looks, and there has been some works also that that say that actually this doesn't work also in practice. But this is a very nice property that with certain translation it seems to hold at least to a certain extent. But of course, this is not the only reason where embeddings were popular. And there are more models. Of course, I focus on Word2Vec. That is one of the most popular, but there was even something before, also based on neural networks, like as early as 2003. But even before that, there has been some similar ideas. And then we have also something after that, like the famous GLOF, that is this one, Pennington et al. 2014, that this is kind of a combination of prediction-based models with count-based models that has been shown also very successful and very popular. So this is all for the most common word embedding approaches, both count-based and predictive models. And now I'm going to move to some special types of word embedding. Or we should better say some ways that there are actually to improve this standard architecture to learn word embedding. So what are these other types of word embeddings that we are going to study? I'm going to focus mainly in 3 different ones, but there are others. But these are probably the most popular ones and the one that has been most successful, like I'm going to move to character-based, knowledge-enhanced, and cross-lingual. Let's start with the character-based word embeddings and what is the main motivation for having character-based models. The main problem of having just a vector space when you have only words is that you can neglect different phenomena in language. That is, first, language is in constant change, so there is new words that are created every time, or new senses of a word, and this is impossible to capture in practice. Not because it's only impossible to gather enough context, because they're going to be always new, but also because in a way it's also kind of inefficient, and it will need a lot of space, or memory to keep all these vectors, even if they are low dimensional. And this obviously can have a negative effect in applications. But then there are also like different settings, like in social media, where there are many misspellings, or people don't use like what we call the official language, and they write in different ways, and often creative ways. And these are not going to be also captured by general word embedding models. And what is a solution for that? A solution for that is take into account the characters. Often the misspellings are going to be very close to the real spelling, to the correct spelling, or there are many cues, especially in agglutinative languages, where, for example, you have suffix or things like that, or some part of the sentences that you combine to create a word. And in this case, this is really, really important, to cover these character-based models, because it's what I'm going to give you the clue, what is the meaning of the word. Like languages, for example, like German, they combine often different words and concatenate into the same token, So if we consider like the token to be our unit, we are going to miss a lot of combination of those words, that maybe they don't occur quite often, in the corpus, Because of that, you can actually leverage characters, and this doesn't mean that we are not going to consider any more words, but many times we are going to consider character in concatenation actually with words themselves. And with this combination, actually, you can get the best of both worlds, where you can model actually words, but then also you are kind of robust, to misspelling and to cover also out of vocabulary words. One of the best examples for that is fast text. That's basically it's the same architecture of Word2Vec, but there is an extension where you actually have also subwords that are actually a combination of characters that gives this robustness, and the ability to model even out of vocabulary words. Another example that is only quite successful is different encodings like a BPE or WordPiece, and this has been much more popular in the recent contextualized embeddings era. So I recommend you to see that video to know more about that. The second type of word embeddings are what we call knowledge-enhanced word embeddings. And here the main idea is basically to use knowledge or lexical resources to improve word embeddings, to improve their quality. And how can we improve the quality using lexical resources? There are many different ways, but the main argument to have this, it is that you have a corpus where you can learn a lot about the co-occurrences, but why not to use already like handcrafted resources that provide a lot of knowledge, for example, WordNet, or even encyclopedic resources like Wikipedia or resources like that you have a lot of information there that you can actually leverage. Many times this information comes in the front of a semantic network, so you have connections like different items, for example, words or senses, they are connected with each other, and you can leverage the connection to actually know the meaning of the word. So for example, if you have a taxonomy about animals, you will know that if you have a tiger, that tiger is going to be very connected with big cats and animals as a whole, no? And this is something that maybe you didn't capture in your corpus, or it can be even complementary, no? So how can you do that? Two main approaches. One is directly you modify the objective function of word embeddings. So if you remember, the objective function is many times something very similar along the lines that you had to predict a word in context. But in this case, perhaps you can add this information from lexical resources and refine this objective function, to integrate this knowledge. And another approach that has been more successful recently is the post-processing, or what is called retrofitting in some papers. In this case, what you do is basically you learn the word embeddings that you were learning before with your corpus, but on top of that, what you're going to do then is refine them. So you are going to check the connections in the semantic network, and then you are going to move words together if they are quite connected in the semantic network, or just pull them apart. Is, for example, you ended up having some words that are similar in your word embeddings by chance or by some artifacts of the corpus. And in addition to retrofitting approaches, a similar idea is the word vector specialization, that in this case what you do is you use lexical resources or other kind of linguistic knowledge or extra information to specialize word embeddings for a particular task. And this is quite relevant, as many times what we want is to have word embeddings that can be helpful in downstream tasks. So if you have some word embeddings that are specialized to be good in that task, that can lead to automatic improvement. So after the knowledge enhanced word embeddings, we have the cross-lingual word embeddings, so what we call cross-lingual or multilingual word embeddings. So what are cross-lingual word embeddings? In the most simple scenario, what we have is two languages. For example, here in this figure we have English and Spanish. And what you want here is to learn a vector space not only for words in English or words in Spanish, but where you have words in English and Spanish simultaneously. So for example, we have here like love and amor, that actually there are translations. In the translation of love in English is amor in Spanish. You want to have to end up close in the vector space, as they actually have pretty much the same meaning. And then also maintain the nice properties what we have in monolingual word embeddings, like similar words are going to be close in the vector space and so on. I'm not going to get into much detail. I'm going to explain a bit the methodology of these cross-lingual embeddings, but if you want to get into more details, I recommend you the book of cross-lingual word embeddings, where you have a lot of information about that and the different approaches. And how can we learn cross-lingual word embeddings? The approaches are often split by the type of supervision that the model uses. So for example, we have sorted here like 4 different types of approaches, where the approaches on the top, they need a higher level of supervision. So let's start with the first, that is a sentence level supervision. Here you assume that you have a document that is translating into 1 or more languages, depending on what you want to your vector space to look like. And then we can reduce actually this supervision to learn word embeddings. And this has been a trend in recent years where some works have shown that actually you don't need that much supervision to learn effective cross-lingual embeddings. And you can learn maybe embeddings that is of a lower quality, but that has also other nice properties, and also the fact that you can learn with a minimal amount of supervision. So one of these approaches is a document level, but here it is stated that you can learn cross-lingual embeddings as well with comparable corpora. So it doesn't have to be actually translated at the sentence level or at the word level, but basically having documents that talk about roughly the same thing. And then one that has been the most popular in recent years, arguably, is the word level supervision. That basically here what you need is just only words that are translated. So this is very easy to find, as you can find, for example, in dictionaries, in bilingual dictionary was the traditional ones, where you can have a word from one language translated into a word in other languages. So these approaches, basically how they work is roughly how it is showed here in this figure, where the first step, if you learn a vector space, as you will learn in the monolingual case, so you have, for example, a corpus in English and a corpus in Russian, and what you want to learn is word embeddings in English and word embeddings in Russian, no? Like using a common word embedding approach. And then what you want to try is to merge one space into the other, but without changing the main properties of the space. So often it's an orthogonal transformation. And finally, also some approaches that they show that you can even have a final step where actually you can actually refine and improve more this alignment where you didn't change the properties of the space. And finally, you have similar approaches, but in this case it's unsupervised. So they show that even you don't need even a dictionary, and you can learn these transformations automatically. So this has been very, very popular. As also has been shown that is an approach that can work even for unsupervised machine translation, where you can have accurate translation without the need for parallel corpora. And finally, we move to the application and evaluation section, where I'm going to try to argue what are the main applications and evaluation procedures for word embeddings, but just give you a very high-level overview of this. So one of the main usages and the most successful, we could say, in recent years is like word embeddings are very useful when they are used as an input for a neural network. So most of the times when you have an NLP task, where you're going to have is an initial layer, what we call even embedding layer, that is going to be composed of the word embeddings. And then you are going to have different layers on top of that. And this is quite useful because then you don't need to randomly initialize the words, but you have already information about the words. And this is especially relevant in settings where you don't have much training data. And for example, maybe in your training data you have, let's say, with our running example, that you have the word tiger, but you don't have the word jaguar. But you know, because tiger and jaguar are close in the vector space, they share some properties. So your neural network actually can infer that the properties that it learned from for tiger, or the sentence where tiger occur in the training set, maybe they can actually extrapolate it to jaguar. And this can be very useful in that way and in many others. No, so it gives this kind of generalization power to neural networks that they wouldn't have otherwise. Then also they are quite useful on their own, and they have been used many by linguists or computational linguists, where they want to investigate a certain corpus and different linguistic phenomena, like for example meaning shift or other properties that you want to study in a corpus. So they are quite handy for that. As I mentioned, they are very practical, they are very easy to use, and you can check similarities very, very easily, or other properties as well. And finally, how can you evaluate this word embedding? So there are many different ways to evaluate, and of course, I'm not going to go into details, but there are too many paradigms. And the first is intrinsic, where you are going to test some properties in your word embedding space, like often it's like word similarity or word analysis that I explained before, but it can be any other characteristics that you want to study in your vector space, to know that it is fulfilling some of the properties that you want the word embeddings to have. But then, because we say that the main application of word embeddings is in downstream applications, so one evaluation protocol is perhaps use these word embeddings in a suite of downstream tasks. Or if you want just word embeddings in a particular task, so you can evaluate in that task, in different data set from that different task. And this is basically all about word embeddings. Hope it was a useful overview, but of course there are many details that I didn't talk about, because this is a field that has a very extensive literature, especially in the last 10 years. So, but hopefully at least I've provided some pointers that you can actually study on your own if you want to get into these details.